Welcome back, everyone. Today, we are diving straight into a fantastic explainer focused on adding and subtracting polynomials. Now, I know what you might be thinking. Whenever people hear the word algebra, it's incredibly easy to feel this sudden wave of math anxiety. And honestly, it makes perfect sense why. We're suddenly dealing with letters instead of just numbers, and it can feel a bit like you're staring at a secret code that you were never actually taught how to read. But at its core, algebra is simply a language. It is a highly practical, everyday way to represent changing quantities in our daily lives, our homes, and our work. It's exactly how we keep track of things when the amounts aren't always set in stone. So today we're going to master how to group these changing quantities together and figure out exactly what we have. Okay, let's dive into this.
Here is a quick look at our roadmap for today's explainer. 1. Anatomy of a polynomial. 2. Grouping like terms. 3. Adding polynomials. 4. Subtracting polynomials. And finally, 5. Real-world polynomials. Let's get to it.
Before we get into the nuts and bolts, I want you to keep a specific question in the back of your mind as we go through these concepts. What does a neighborhood sorry store have to do with algebra? Seriously, imagine for a second that you're standing in front of a real, packed, maybe even slightly messy store shelf. You've got stacks of biscuits, rows of drinks, boxes everywhere. It might seem incredibly abstract right now, but as you'll see, those intimidating algebraic letters and numbers are literally just tools we can use to track that exact kind of daily business inventory. Section 1. Anatomy of a polynomial. Building the foundation. Okay, so the absolute smallest unit in algebra is called a term. Now, what's really interesting about this is how beautifully simple a term actually is when you break it all down. It can just be a plain old number, like an 8. It can be a letter representing some unknown amount, or, very often, it's a combination of both of those things, tightly glued together by multiplication, like a 5x or a negative 3y. Think of a term as a single, packaged item sitting on a store shelf. It is one distinct, unbroken unit of inventory. You pick it up, you move it around, and it stays perfectly whole. Now, inside those terms, you're usually going to find a variable. Variables are those letters, typically an X, a Y, or an A. I know they often scare people, but listen, they are literally just placeholders for things we don't know the exact number of yet. In a real-life livelihood setting, let's say X represents physical packs of biscuits and Y represents bottled drinks. The letter just stands in for the physical object until we go back and do the final count. That's all it is. Sitting right next to that variable is usually a coefficient. This is the numerical factor of a term. So in the term 7x, the number 7 is your coefficient. It's playing a very, very simple role. It just tells us how many of those variables we actually have. If x is a pack of biscuits, the coefficient 7 tells us, hey, we have exactly 7 of those packs. It really is that straightforward. And here is a fun little insider tip. If you ever just see a plain X without a number in front of it, there is actually a hidden invisible 1 standing right there next to it. You always have at least 1. Then we have the constant. This is a term completely without a variable attached to it. Think of a plain 6 or a negative 4. We call it a constant because its value is steady, it's predictable, and it's unchanging. Without a variable attached to it, a 6 will always just be a 6. Actually, think of them as the anchors of your equation. It stands completely alone, and it's completely independent of whatever x or y might be doing. So let's bring all those definitions together to form our main topic for the day, the polynomial. A polynomial is simply an algebraic expression made up of the terms we just learned, joined together by addition or subtraction signs. It's a chain of terms. If a term is a single train car, the polynomial is the entire train hooked together. And just like a real train, where you can add cars to make it longer or decouple cars to make it shorter, you can add or subtract terms to completely change the length of your polynomial. Section 2. Grouping like terms, the golden rule. Before we do anything else, we have to apply the golden rule of grouping. Just think of the classic apples and oranges comparison. Like terms have the exact same variable and the exact same exponent, like 3x and 5x. Because they are absolutely identical in their variables, they belong to the same family and you can easily group them together. Unlike terms, however, have completely different variables, like 3x and 3y, or they have different exponents. You simply cannot group unlike terms. I mean, you can add apples to apples all day long, but you can't logically combine an apple and an orange into a single, brand new piece of fruit, right? Okay, let's pause for a quick check to see if you're following along with me. I want you to think about this specific scenario. Can 4x and 4x squared be combined? Really think about what we just discussed regarding the strict rules for like terms. They both definitely have an x, and they both clearly have a 4. So what do you think? Take a second to lock in your answer.
The answer is a definitive, absolute no. If you said no, you hit the nail on the head. These are unlike terms and absolutely cannot be combined. Why? Well, because they have different exponents. The first is an x to the invisible power of 1, and the second is an x to the power of 2. That tiny elevated exponent changes absolutely everything. It means they belong to completely different families, and you cannot mix those families together under any circumstances whatsoever. Moving on to section 3, adding polynomials, combining forces. All right, let's get into the actual operations. Here are the 3 simple steps for addition. First, carefully group your like terms together, family with family. Second, add their coefficients, and remember, those are just the numbers out front. Third, and this is absolutely crucial, keep the variable part exactly the same. Let's see how this builds into solving actual equations.
Let's put this into practice right now. We're adding the polynomial 3x plus 5 to the polynomial 2x plus 4. Following our steps, first, we group the x family together, so we take the 3x and the 2x. Then we group our constants, that plain numbers, together, so we take the 5 and the 4. Now we just add the coefficients of the x's, 3 plus 2 to get 5x, and we add the constants, 5 plus 4 to get 9. Our final, beautifully simplified answer is just 5x plus 9. Easy, right? Let's try one that looks just a little bit harder at first glance because it has exponents and negative signs. But do not let it intimidate you. The rules haven't changed one bit. We're going to apply the exact same logic. First, we group the x squared family. 2x squared plus 1x squared gives us 3x squared. Next, we group the regular x family. 4x minus an x leaves us with 3x. Finally, our constants. A negative 3 plus a positive 7 gives us a positive 4. Step by step, family by family, it cleans up perfectly to 3x squared plus 3x plus 4.
Section 4, subtracting polynomials, the tricky part.
The source material for today's explainer frames this next concept beautifully as the sign change challenge. And this is the part where people usually trip up. So the crucial point is mastering this specific challenge. When you subtract one polynomial from another, the biggest pitfall to avoid is just subtracting the very first piece you see. You aren't doing that. You are actually subtracting the entire second group, every single piece of it. So here is the exact step-by-step mechanism to conquer the challenge. Step 1. Change the signs of every single term in the polynomial being subtracted. If a term is positive, you must make it negative. If it happens to be negative, you flip it and make it positive. Step 2. Once you have successfully flipped every single one of those signs, something magical happens. The dreaded subtraction problem actually turns into a friendly, simple addition problem, and you just combine like terms exactly like we did in the previous section. Let's walk through it together. We have 5x plus 8 minus the entire polynomial 2x plus 3. We apply the sign change challenge to that second group. The positive 2x becomes a minus 2x. The positive 3 becomes a minus 3. Now, we just group and combine. Let's do it in our heads. 5x minus 2x gives us 3x. And our constants, 8 minus 3 gives us a positive 5. Our final, simplified answer is 3x plus 5. That sign flip really is the magic key to unlocking subtraction. And our final section, section 5, real-world polynomials, the sorry store. Let's bring everything we've learned full circle and set the stage using our neighborhood store from the beginning. We'll use X to represent our packs of biscuits and Y to represent bottled drinks. The plain constants will represent miscellaneous items. Now, imagine it's a very busy Tuesday. On Monday, we close the shop with our inventory sitting at exactly 5x plus 3y plus 2. But this morning, a delivery truck pulls up and unloads brand new stock, adding 2x plus y plus 5 to our store. Throughout the day, customers are coming in and out, constantly buying items off the shelves. So we sell, meaning we subtract, 3x plus y plus 1. We now have all of that incoming and outgoing daily chaos written as clear, organized, mathematical phrases. And here is the grand finale calculation to find out exactly what is left on our shelves at the end of the day. First, we figure out our total stock by adding Monday and Tuesday together. We combine our x's, our y's, and our constants to get a grand total of 7x plus 4y plus 7. But wait, we have to subtract what those customers bought. We apply the sign change challenge to the sold items. 7x minus 3x leaves 4x. 4y minus y leaves 3y, 7 minus 1 leaves 6. By using polynomial addition and subtraction, we instantly and perfectly know our remaining inventory is exactly 4x plus 3y plus 6. Look at that. We've successfully managed a real, thriving business using algebra.
And that brings us to the end of today's explainer on adding and subtracting polynomials. You've seen how simple terms build into powerful polynomials, how grouping brings order to chaos, and how these mathematical operations can literally solve actual, everyday business problems. So, I'll leave you with this final provocative thought. Look around you today. Where else in your daily home, work, or community life can algebra represent changing quantities? Once you start looking for the x's and y's out there in the real world, you'll realize you've been doing algebra all along. Keep calculating, and we will see you next time.